Hello everyone. Once again I welcome you to the video lecture on first part of the second module, that is testing on transformers. In last video we were discussed the polarity test on transformer. In this video our discussion begin with one more test on transformer, that is Sumpner test. This test is also called as back-to-back test or regenerative test. The Sumpner test, it gives the information regarding the maximum temperature rise in a large transformers, which is to be determined by using the full load test. Sumpner test or back-to-back test is one more method for determining the transformer efficiency, voltage regulation and heating under loaded condition. There is one more test in order to determine the transformer efficiency and regulation, so that is open circuit and short circuit test. And this open circuit and short circuit test, it gives the determination of the parameters of the equivalent circuit, but it cannot give the uh, heating information. Thus, the Sumpner test give more accurate result of regulation and efficiency than OC and SC test. Sumpner test or back-to-back test can be employed only when two identical transformers are available. So that too, both transformers are connected to supply such that one transformer is loaded to on another transformer. So let us see the constructional feature of the Sumpner test in order to determine the efficiency of the transformers. This is the electrical connection which represents Sumpner test on transformer. It consists of two transformers, both are identical, transformer T1 and a transformer T2. The primaries of the two identical transformers are connected in parallel across the supply. See, the AB be the primary winding of the transformer T1, CD be the primary winding of the transformer T2. These two primary windings are connected parallelly across a supply, and a wattmeter is connected across these primary winding of two identical transformers, and the secondaries of these two identical transformers which are connected in series in such a way that the EMFs which are induced across these two secondary windings are opposite to each other. A wattmeter W2 is connected across the secondary winding of these two identical transformers, and the ammeter is connected. So the secondaries of these two identical transformers which are connected in series, so that is to be connected to the one more transformer secondary terminal. So this transformer, it is called as the low rating transformer. So this is the connection of the Sumpner test on transformer. Initially it operates under no load condition. Under no load condition, the current drawn from V1 is 2 times I0, where I0 is the no load current of each transformer. The input power which is measured by wattmeter W1 is equal to iron losses of both transformers. The iron loss per transformer, it is nothing but the half of the iron loss of both transformer. The iron loss of both transformer is W1, then iron loss of each transformer is, that is P suffix I is equals to W1 divided by 2. Now a small voltage which is injected into the secondary with the help of a low voltage transformer. So this voltage V2 is adjusted so that the rated current I2 flows through the secondary of two identical transformers which are connected in series. So in this case, the both primary as well as secondary carries the rated current. Since the wattmeter W2, it reads the full load copper losses of both the transformers. So here also the copper loss per transformer, which is given by, that is P suffix Cu is equals to W2 divided by 2. From these above test results, so that is the iron loss of per transformer and copper loss of the per transformer. So the full load efficiency of each transformer can be determined. So which is determined by using the formula, that is percentage full load efficiency of each transformer, that is equals to output divided by output plus the iron loss of each transformer plus copper loss of each transformer into 100. The output of the each transformer, which is calculated by the VA rating into its power factor. Now this is about the Sumpner test on transformer, how the Sumpner test is to be carried out in order to determine the efficiency of the transformer. Now it has several advantages and disadvantages. So let us discuss the what are the advantages and disadvantages of this Sumpner test on transformer. So advantages, the first advantage is that the transformers are tested at full load conditions. So obviously, so in order to calculate the copper loss, so we need to load the secondary of the transformer. So till full load condition, so we used to conduct the test. So since the transformer are tested at full load condition, so this is one more advantage on the Sumpner test on transformer. The second advantage is that from this transformer we used to calculate the maximum temperature rise. So that is heat run test can be conducted on the two transformers. Then one more advantage is that the equivalent circuit parameters can be obtained. So the equivalent parameters can also be obtained by the OCSC test, and this test is also helpful for the obtaining the equivalent circuit parameters of the transformers. The regulation and efficiency at any load and power factor can be determined from this test. The core losses and copper losses occur simultaneously. So once the core loss will obtained, so during the loading of the secondary winding of a transformer, then we can get the copper loss. So this will be obtained simultaneously. The power required to carry out the test is very small. So whatever be the secondary of the two identical transformers are loaded by the water, the low voltage transformer. So since the power required to carry out such test is very small. By varying I2 using regulating transformer, copper losses at any load condition can be obtained. So by varying I2 means what? So we used to inject whatever be the voltage is to be injected by the low voltage transformer. So that is to be varied. So once that voltage is varied, the I2 is varying, then the copper losses at any load condition that can be determined. This is one more advantage. That means that so we used to auto the change I2 by using the regulating transformer. What is the regulating transformer here? So that is the low voltage transformer. So that is connected to the secondary winding of two identical transformers. So these are some advantages on the Sumpner test on transformer. Then what are the disadvantages on Sumpner test on transformers? So first disadvantage is that so two exactly opposite transformers are necessary, which is very difficult. So this is one more disadvantage, that is initial cost is high because it requires two transformers, hence not economical. So in order to carry out such test, we need two identical transformers. It is more economical. So so these two are the disadvantages on Sumpner test on transformer. Let us study separation of hysteresis and eddy current losses in single phase transformers. Core losses on transformers. So this is the combination of hysteresis and eddy current losses. Both losses occur within the core itself, that is the magnetic material. The power drawn from the supply under no load condition, that can be approximately taken as the total iron losses. The total iron loss is the combination of hysteresis loss and eddy current loss. That is, iron loss is equals to hysteresis loss plus eddy current loss. Hysteresis loss, it is proportional to the flux density and the frequency. So here the flux density, it is being kept constant. Then the hysteresis loss is proportional to the frequency. Just remove the proportionality. So hysteresis loss is equals to K1 into F. K1 is the proportionality constant. Similarly, the eddy current loss, which is proportional to square of the flux density and square of the frequency. Here also the flux density, it is being kept constant. So then the eddy current loss, it is proportional to square of the frequency. Again removing the proportionality. So then it becomes eddy current loss, that is equals to K2 into F square, where K2 be the proportionality constant. Here K1 and K2 are constants for a particular transformer. Then the applied voltage, that is V1, that is equals to E1, and again that is equals to the induced voltage across the secondary winding of a transformer. What is the induced voltage across the secondary winding of a transformer? That is, this is the EMF equation of a transformer, that is 4.44 F B AI TPH. So just here 4.44 is the constant. Again the flux density is the constant. The area of cross section of a iron core is a constant. Turns per phase is again constant. Then so here, so you just bring this F into left hand side, that this becomes V divided by F is equals to 4.44 B AI into TPS. That means you just keep the V by F as a what? Constant. Thus, to maintain flux density constant during the experiment, it is essential to keep V by F constant from all variation of frequency. So here, in order to maintain the flux density constant, we need to keep the V by F, that is, this ratio is to be maintained constant for all variation of frequency. Here the total iron loss, so that is given by again the combination of hysteresis and eddy current loss. So the hysteresis loss is what? K1 into F. Eddy current loss is the what? K2 into F square. Just put here, that is W is equals to K1F plus K2F square, or so just from this you just remove F common, then bring that F into left hand side. So this becomes W divided by F is equals to K1 plus K2F. This is the equation is in the form of what? The straight line equation. What is the straight line equation? That is y is equals to mx plus c, or you can quote any notation, that is ma plus b. So thus the plot W by F versus F will be a straight line as shown in the figure, from which the constant K1 and K2 can be found. How the constant K1 and K2 can be found here? See, so this is the similar curve, so that is the straight line. you know the straight line, that is equation of the straight line is what? That is y is equals to mx plus c. So compare that y is equals to mx plus c in this equation. So here y it represent, that is w divided by f, and m it is represented as what? This is what? The k2, and x it is what? The frequency f. Then c is the constant, this is what? K1. So just to draw the graphical representation of this equation, so it becomes what here, that is w by f versus the frequency. So if w by f, that is k1 is equals to 0, w by f is equals to k2 f. In this case, the straight line it starts from what? Origin. So if k1 is not is equals to 0, that is w by f is equals to k1 plus k2 f, such type of equation. So there will be some k1 value. So this is the k1 value. See, this is the k1 value. And what is k2 here? K2 it is nothing but this slope of the straight line. Then how the slope of the straight line can be obtained? Just point any 2 points on the straight line. So just name that point with two coordinate axes, that is just I will just consider here one point, that is x1 y1. I just consider here one more point x2 y2. Just plot the slope between these 2 points. That slope it represent, that is y2 minus y1 divided by x2 minus x1. So in this way, just used to calculate the value of k2. Then you know the frequency, then substitute in this equation, then you will get the what? The total iron loss. This is the experimental setup and procedure in order to separate the hysteresis and eddy current losses. So this is the circuit representation. See, it consists of the transformer. This is the transformer. By this transformer, so we are going to conduct a test. Then we'll determine the iron loss. This wattmeter it determines the iron loss. So from this iron loss, we used to separate hysteresis and eddy current losses. Now see, a wattmeter it is connected uh, across the primary winding of a transformer. The secondary winding of a transformer it kept open, because from the open circuit test we used to calculate the iron loss. See, you know the supply which is fed to the primary winding of a transformer, so that is what? The variable voltage and variable frequency. So that is given by the what? The mg set. That is nothing but a motor and generator set. So that means this generator it supposed to give the supply to the what? The transformer. So that to what? The variable frequency. How the variable frequency can be obtained here? By varying the supply across the what? Field winding of the generator or alternator. So then you will get the variable frequency across the water, the supply to the water, the primary winding of a transformer. Now what procedure is to be followed here? That is, connections are made as per the circuit diagram. Supply is given by closing the DPST switch. So once this DPST switch is closed, supply is fed to the water, the transformer. The DC motor is started by using the 3-point starter. So this is the 3-point starter. The DC motor is started and brought to rated speed by adjusting its field rheostat. So this is the field rheostat of the DC motor. By adjusting this field rheostat, uh, the motor is to be bring into what? The rated speed. By varying the alternator field rheostat gradually, the rated primary voltage is applied to the transformer. See here. So the alternator field winding is varied by the field rheostat gradually. So in order to obtain the rated primary voltage, across the what? The transformer. The frequency is varied by varying the motor field rheostat, and the readings of frequency are noted, and the speed is also measured by using the tachometer. The above procedure is repeated for different frequencies and the readings are tabulated. The motor is switched off by opening the DPST switch after bringing all the rheostats to the initial position. So this is the what procedure to obtain the iron loss by conducting the open circuit test on the transformer. Now, what data are tabulated here? This is the tabulation. So first we used to tabulate speed in RPM. So this is the motor speed and frequency. So this is given by the water, the alternator by varying the field winding of an alternator. The variable frequency is to be noted here. Then with respect to variable frequency and the voltage is also noted down here. Then wattmeter reading, so that is to be noted here. Then iron loss, so this wattmeter reading itself, it gives the what? Iron loss here. So then Wi divided by F. So this is the Wi, it is nothing but the iron loss. So that is what? The wattmeter reading. So this divided by F, so that is to be what? Tabulated here. So next we used to what? Plot the graph Wi divided by F versus the frequency. This is the what? Nature of the graph you will get. So some formulas are used here. So that is frequency. So we used to calculate frequency by using the formula P into Ns divided by 120. So here P is the number of poles, Ns is the what? Synchronous speed in RPM. Then you know the hysteresis loss, how to calculate the hysteresis loss. So that is to be calculated by using here. So that is A into F. So in watts. So here A, how to obtain this A? So A can be obtained from the graph here. So this is the A value. So from origin to water, so this point. So this is the water A value. So you can obtain from this value from the water graph. So frequency, you know the frequency. So here for different frequency we conducted the test. So used to calculate the hysteresis losses for the water different frequencies. Then eddy current loss can be calculated by We, that is equals to B into F2. So sorry, this is B into F square. So B, it is nothing but a slope of the tangent drawn to the curve. So C, so this is the what your straight line. Just you need to what draw one tangent to this slope. Then you used to calculate the slope of this straight line. So that represent what it is B. Then the iron loss, it is the combination of the hysteresis loss and eddy current loss. Then so Wi divided by F, that is equals to what? So just to take the what? These two combination, that is A plus B into F. Here the constant A is distance from the origin to the point. So here A, it is nothing but so distance from the what? Origin from a what? Point A. Line the cuts the y-axis in the graph between Wi divided by F and frequency F. The constant B is, and here the constant B is also calculated by using the formula that is del Wi divided by F divided by del F. That is so this one del Wi divided by F. So that is divided by what? Del F. From here to here, this is what del F. So here I just drawn the water slope. So from this slope, so just I consider this is the what? Del Wi divided by F. And what is del F? Del F, it is nothing but this line. So this gives the what? The constant B. That is, you just draw the slope here, slope line here. That is slope of the tangent drawn for this straight line. Just point this 2 points on the straight line. So just consider here one point. Just I will show you. Just consider the two points here. So what are the points is to be considered? Just consider here is the one point. So here is the one more point. So just draw the tangent to this curve. So what is the tangent? You just draw here. I just show you the how the tangent will be drawn here. Just draw from this point to here. How the b is to be calculated? See how the b is to be calculated here. So that is b is to be calculated by, that is ratio of del wi divided by f divided by del f. Del wi divided by f, it is nothing but what? So this is the what? Del wi divided by f. Which one? So this one. So from here to here, from here to here, that is del wi divided by f, and from here to here, so this is nothing but del f. These two ratios, it gives the constant b. So this is about the how the Sumpner, how the losses are separated, that is hysteresis and eddy current losses from the water total iron loss, and what are the formulas are used in order to calculate the hysteresis loss and eddy current loss. So in next video we'll come up with some more bits on the second module. Till then, take care. Thank you.